Here we are at the 0.2 number 2 set of notes. We're looking at more graphing rational functions, and it kind of just also along with the horizontal asymptote and vertical asymptote, we're going to go ahead and add some things like trying to find the x-intercepts for a particular rational function. And how this works when we're trying to find the x-intercepts, again, that just means where it's crossing your x-axis. That's why it's literally called an x-intercept. It's intercepting the x-axis. So if you just had like a little graph, here is our x-axis, here's our y. You know, where is it crossing? Maybe we're looking for that point right there. So that's really what we're trying to find here. And how we do that, it's also known to be finding the zeros. How we do that with a rational function when it's equal to 0 is it's simply that we just take the top piece, just the top piece, and set that equal to 0. And the reason why this works, just a little side note, is if we have ax plus b over cx plus d is equal to 0. And by the way, a, b, c, and d are just some real numbers. So they're just, you know, like 2, 4, whatever, -8, doesn't matter. The reason, though, why this definition actually works when we're trying to find x-intercepts is if we were to go ahead and try and solve for x here, again, trying to look for that x-intercept, we would go ahead and multiply both sides by this cx plus d on both sides. And on the left, the cx plus d would cancel out, leaving us with this ax plus b. On the right, that cx plus d times 0, well, that still just comes out to be 0. And that doesn't really change anything, except just makes then that ax plus b is equal to 0. And from here, you'd be able to solve for your x-intercept. So that's really why this definition actually works. As you're trying to find the x-intercepts. And that's why we can kind of use that shortcut. Well, if you're trying to find the x-intercepts, just take the top, set it equal to 0. Moving forward, for example 1, it's asking find the x-intercepts for this particular function. Well, again, we don't really care at all about this bottom piece. We only really care about this top. So we're going to go ahead and take our x plus 2 times 2x minus 3 and set him equal to 0. Using that zero product property, it pretty much just says we can break each one up and set each individual piece equal to 0. So we have our x plus 2 is equal to 0, and we have this 2x minus 3 is equal to 0. And then just solving each one like their own. So we have this guy comes out to be x is equal to -2. This one over here, we'd end up with 2x is equal to 3. Divide 2 on both sides. X just comes out to be 3/2. So in other words, we should see an x-intercept at -2, comma, and this one, 3/2, comma. Now, when we think about an x-intercept, by the way, like this, if you were just to leave your answer as x equals -2, or x equals 3/2, that's technically not the most correct answer, because what you're saying when you state this as like a final answer is it's actually a line. And when we're talking about x-intercepts, an intercept is actually just a point. So it's literally intercepting this x-axis at a specific point, not a line. And as a result, well, if we just look at this, if it's crossing this x-axis, what are always the y values? Well, your y values, you're not going up, you're not going down any, and as a result, every single time you're crossing your x-axis or looking for your x-intercepts, your y values will always just be 0. So that's why it's actually, your correct answer is a final point. So these should always be whatever x that you found, comma 0, and then, yeah, same thing for this one. We'd have 3/2, comma 0. So again, that is the definition for x-intercepts and example 1.